Welcome to this problem walkthrough. In this session, we'll explore problem number 298, titled Binary Tree Longest Consecutive Sequence. This is a fascinating problem that challenges your understanding of trees, recursion, and algorithms. Let's dive in and break it down step by step. In this problem, we are tasked with finding the length of the longest consecutive sequence path in a binary tree. A consecutive sequence path is a path where the values of consecutive nodes differ by exactly 1. Importantly, this path can only traverse along parent-to-child connections, whether through the left or right child. The length of such a path refers to the number of nodes included in the sequence. For input, we are given the root of a binary tree, where each node contains an integer value. The output will be an integer representing the length of the longest consecutive sequence path found in the tree. To understand this problem better, let's look at an example. Consider this binary tree where the root node has a value of 1, and it has a right child with the value 3. The node with value 3, in turn, has two children, a left child with value 2 and a right child with value 4. The node with value 4 further has a right child with value 5. In this case, the longest consecutive sequence path is formed by the nodes 3, 4, and 5. The values in this path differ by exactly 1, forming a valid sequence, and the length of this path is 3. Therefore, the output for this example is 3. Here's another example. This binary tree starts with a root node of value 2, which has a right child with value 3. The node with value 3 has two children, a left child with value 2 and a right child with value 4. The node with value 4, like before, has a right child with value 5. Again, the longest consecutive sequence path is 3, 4, and 5. The sequence forms a valid path since the values differ by exactly 1, and the length of this path is 3. Thus, the output for this example is also 3. Now let's consider a simpler case. If the binary tree consists of just one node with the value 1, the longest consecutive sequence path will simply be the single node itself, since there are no other nodes to form a sequence with. The length of the path in this case is 1, as it only contains one node. Therefore, the output for this example is 1. Finally, let's discuss some important constraints and edge cases for this problem. The number of nodes in the tree can range from 1 to 10,000, and the value of each node can range from -1 billion to +1 billion. For edge cases, consider a single node tree. The output will always be 1, as there are no consecutive paths possible. In a tree where no consecutive values exist, the output will also be 1, since no valid paths can be formed. Additionally, in trees with multiple branches, only the branch that contains the longest consecutive path will determine the output. Even if all node values in the tree are consecutive, but they appear in different branches, only one branch will form the longest sequence. To begin solving this problem, one straightforward approach we might consider is the brute force method. Here, we use depth-first search, or DFS, to traverse the entire tree. For every node, we check all possible paths to see if they form a consecutive sequence. The idea is simple: we iterate through every potential path, calculate its length, and return the longest one that meets the condition. However, this method has its drawbacks. It doesn't focus on whether the paths are consecutive, so we end up repeating a lot of computations unnecessarily. As a result, the time complexity becomes n squared, which is impractical for large trees. While it's easy to implement, the trade-off is that it's computationally expensive and inefficient for trees with many nodes. On the positive side, the space complexity is just h, where h is the tree's height, since the recursion stack is the primary memory cost. Now, let's make this process more efficient by using an optimized approach. Here, we still use DFS but introduce a mechanism to keep track of the current consecutive sequence length as we traverse the tree. The key idea is to check if the current node forms a sequence with its parent. If the current node's value is exactly 1 greater than its parent's value, we extend the sequence. Otherwise, we reset the sequence length to 1. To implement this, we define a helper function that takes the current node, the parent node's value, and the sequence length so far. If the node is null, we return the current sequence length. Otherwise, we update the sequence based on whether the consecutive condition is met, and then recursively explore the left and right subtrees. This approach ensures that we visit each node exactly once, giving us a linear time complexity of O, n. It's also space efficient, with O, h, due to the recursion stack, and avoids redundant computations by focusing only on valid consecutive sequences. Another way to solve this problem is by using a bottom-up DFS approach. Here, instead of passing information about the sequence length downwards, each node calculates the maximum sequence length starting from itself and sends this information upwards to its parent. This method flips the direction of how we process the tree, aggregating results from the children before making decisions at the current node. While it achieves the same time complexity of O, n, and space complexity of O, h, as the optimized top-down approach, it can be more challenging to implement. Debugging this method is often trickier as well, since the logic of aggregating results requires careful handling to ensure correctness. While it's a viable option in terms of efficiency, the additional complexity makes it less intuitive compared to the top-down DFS. The chosen strategy for this problem is the optimized top-down DFS with consecutive tracking, and there are several reasons for this choice. First, it's efficient, as we achieve linear time complexity by visiting each node only once and maintaining the current sequence length dynamically. Second, it's straightforward to implement compared to the bottom-up approach, which can be harder to debug. Third, it scales well for large trees, as it balances simplicity and performance with minimal space requirements. The key insight here is that we don't need to store or recheck all paths. Instead, by propagating the sequence length as we traverse and comparing node values in real time, we can efficiently determine the longest consecutive sequence. Compared to the brute force method, which is computationally expensive, and the bottom-up approach, which is less intuitive, this strategy offers the best balance of simplicity, efficiency, and scalability, making it the ideal solution for this problem. In this problem, we're tasked with finding the longest consecutive sequence in a binary tree. A consecutive sequence is defined as a path where each node's value increases by exactly 1 compared to its parent. The path has to follow parent-child connections, and it can start from any node. To solve this, we first consider a brute force approach using depth-first search. The goal is to explore all paths in the tree and check if they form a consecutive sequence. We'll define a recursive helper function, DFS, which takes 3 parameters: the current node, the value of its parent, and the length of the current consecutive sequence. If the current node is null, we simply return 0, as there's no sequence to process. This setup allows us to systematically traverse the tree and evaluate each node's contribution to a potential sequence. Now, within the DFS function, we check whether the current node continues the consecutive sequence. If the node's value equals its parent's value plus 1, we increment the length of the sequence. Otherwise, we reset the sequence length to 1, since the consecutive pattern is broken. Next, we recursively call the DFS function for both the left and right children of the current node, passing along the updated sequence length where applicable. As we traverse, we track the maximum sequence length using a global variable, max_length. This variable is updated whenever we find a longer consecutive sequence. Once all nodes have been processed, the value of max_length will represent the longest consecutive sequence in the tree. This approach ensures that every possible path is explored, and the comparison between each node and its parent allows us to efficiently determine where sequences continue or reset. The global variable max_length plays a critical role in this algorithm by keeping track of the longest sequence found during the traversal. This avoids the need for additional passes through the tree. The binary tree itself is represented as nodes, each containing a value and pointers to its left and right children. In terms of complexity, the algorithm is efficient. The time complexity is O, n, as each node is visited exactly once during the DFS traversal. The space complexity is O, h, where h is the height of the tree, due to the recursive call stack. We also need to consider edge cases. For example, if the tree is empty, the result should be 0, since there are no nodes to form a sequence. In a tree with only one node, the longest consecutive sequence is simply the node itself, with a length of 1. In cases where no 2 adjacent nodes satisfy the consecutive condition, the result should still be 1, since each individual node forms its own sequence of length 1. For left-skewed or right-skewed trees, the algorithm works seamlessly because it explores all child nodes recursively, ensuring no path is overlooked. To illustrate, consider a tree with the structure where the root node is 1, with children 2 and 3, and 2 further branching into 3 and 4. Starting from the root, we initialize the sequence length to 1. Moving to the left child, 2, we see that it continues the sequence from 1, so we increment the length to 2. From 2, we move to its left child, 3, which also continues the sequence, bringing the length to 3. This demonstrates how the algorithm tracks and extends the consecutive sequence as it traverses the tree. When backtracking to explore the right child of 2, which is 4, we find that 4 doesn't continue the sequence from 2. Thus, the sequence length resets to 1. Similarly, in the right subtree of the root, the node 3 does not follow consecutively from 1, so the sequence length resets again. After completing the traversal, the global max_length variable holds the value 3, which represents the longest consecutive sequence found in the tree, corresponding to the path 1, 2, 3. To optimize this approach further, we could use an iterative DFS or BFS to avoid recursion stack overflow in very deep trees. Additionally, pruning subtrees that cannot possibly yield a longer sequence than the current max_length can save unnecessary computation. These optimizations make the algorithm robust and scalable for larger or more complex trees. Here, we start by defining the treenode class, which represents a single node in the binary tree. Each node has a value, and optionally a left and a right child. Then, we define the solution class, which contains the method longestConsecutive. This method will calculate the length of the longest consecutive sequence in the binary tree. The function first checks if the root is null, and if so, it returns 0 since there's no sequence to analyze. Next, we initialize a variable self.max_length to track the longest sequence we've found so far. Inside the method, we define a helper function called DFS, which performs a depth-first traversal of the tree. This helper takes 3 parameters: the current node, the value of its parent node, and the current length of the consecutive sequence. Inside the DFS function, we first check if the current node is null, and if it is, we simply return because there's nothing more to process. Otherwise, we compare the current node's value with its parent's value plus 1. If they form a consecutive sequence, we increment the length. If not, we reset the length to 1 since the sequence is broken. Finally, we update the global maximum length with the greater value between its current value and the updated length. Next, the DFS function recurses into both the left and right children of the current node, passing along the current node's value and the updated length. This ensures that we explore every possible path in the tree. After defining DFS, we call it starting from the root node. For the parent value, we use root.val1 to ensure that the first comparison always starts a new sequence. We also initialize the length to 0. Once the entire tree has been traversed, the function returns self.max_length, which now holds the length of the longest consecutive sequence in the binary tree. This approach ensures that we efficiently explore all possible paths while keeping track of the longest sequence encountered. Here, we start by defining the structure of a binary tree node using a simple class called treenode. Each treenode object contains an integer value, along with references to its left and right child nodes. There are 3 constructors provided: one default constructor, one for initializing a node with just a value, and another for initializing a node with a value and its left and right children. Next, we define the solution class, which contains the logic for solving the problem. Inside this class, we declare a private variable, maxLength, to keep track of the longest consecutive sequence found so far. The main method, longestConsecutive, takes the root of the binary tree as input. If the root is null, we immediately return 0, since an empty tree has no consecutive sequence. Now, if the root is not null, we initialize maxLength to 0 and call a helper method named DFS, short for depth-first search, passing the root node, a placeholder value of root.val1, and an initial sequence length of 0. This DFS function is designed to explore the tree recursively. Inside the DFS method, we first check if the current node is null, and if so, we simply return. Otherwise, we determine whether the current node is part of a consecutive sequence by comparing its value to the expected next value, parent val plus 1. If it matches, we increment the sequence length, otherwise, we reset the length to 1. We then update the global maxLength variable to ensure it always holds the longest sequence found so far. Finally, we recursively call DFS on the left and right child nodes, passing the current node's value as the new parent val, along with the updated length. This recursive process continues until all nodes are visited, and we return max length as the result. To solve this problem, we start by traversing the binary tree using depth-first search, or DFS. In this example, the tree is a simple consecutive sequence, 1 connects to 2, which connects to 3. Initially, we set up our variables. We begin DFS at the root node, which has a value of 1, and initialize parent_val to 0, length to 0, and a global variable max_length to 0 to keep track of the longest sequence. At node 1, since parent_val plus 1 equals the node's value, which is 1, we increment the length to 1 and update max_length to the maximum of its current value in the new length, resulting in max_length equals 1. We then proceed to the right child, node 2. At node 2, the condition parent_val plus 1 equals the node's value, which is 2, holds true, so we increment the length to 2. We then update max_length to the maximum of its current value, 1, and the new length, which becomes max_length equals 2. Next, we recurse into node 2's right child, node 3. Here, the condition parent_val plus 1 equals the node's value, 3, is also satisfied, so length increases to 3. We update max_length again, which becomes max_length equals 3. Since node 3 has no children, the traversal ends for this path, and the final result for this example is a max_length of 3. Now let's examine a tree with mixed consecutive and non-consecutive values. The root node is 2, which has left and right children, 3 and 4. We start DFS at the root, with parent_val initialized to 1, length set to 0, and max_length at 0. At node 2, parent_val plus 1 equals 2, so we increment length to 1 and update max_length to 1. From here, we explore both left and right subtrees. Starting with node 3 on the left, parent_val plus 1 equals 3, so length increases to 2, and max_length updates to 2. Since node 3 has no children, we return and explore node 4 on the right. Here, the consecutive condition breaks, so length resets to 1. We then recurse into node 4's children. For node 5, which is the left child of node 4, the condition parent_val plus 1 equals 5 holds true, so we increment the length to 2. However, max_length remains 2, as it is already the maximum. Node 5 has no children, so we return to node 4 and explore its right child, node 6. At node 6, the condition breaks again, and length resets to 1. Since node 6 also has no children, the traversal for this tree ends. The longest consecutive sequence in this tree is from node 2 to node 3, with a max_length of 2. Finally, let's analyze a tree with no consecutive sequences. The root node is 10, with left and right children 5 and 15. Starting DFS at the root, parent_val is initialized to 9, and since parent_val plus 1 does not equal 10, the length resets to 1. We update max_length to 1. Moving to node 5 on the left, the condition fails again, so length resets to 1, and with no children, we return to the root. Exploring node 15 on the right, the condition also fails, resetting length to 1. Node 15 has no children, so the traversal ends. Here, the longest sequence is just a single node, resulting in max_length equals 1. Overall, the key takeaway is that the DFS approach efficiently tracks consecutive sequences by incrementing length when the sequence continues and resetting it when it breaks, while ensuring that both left and right subtrees are fully explored. The time complexity of this solution is O(n), where n is the total number of nodes in the binary tree. This is because the algorithm uses a depth-first search traversal, visiting each node exactly once. During this traversal, the DFS function is called recursively for both the left and right children of each node. Each call performs a constant amount of work, such as checking conditions, updating the current sequence length, and comparing it with the global maximum. Since no node is revisited, the total number of calls is proportional to the number of nodes, resulting in O(n). Even the base case checks, which determine whether a node is null, are part of the traversal and do not add additional computational overhead. This efficient traversal ensures the algorithm's linear runtime. Now, looking at the best, average, and worst case scenarios, the time complexity remains O(n) across all cases. In the best case, such as a tree with only one node, the algorithm still processes that single node. In the average case, often represented by a balanced binary tree, all nodes are visited once during the DFS traversal. Similarly, in the worst case, where the tree is skewed and resembles a linked list, every node is still visited exactly once. Thus, regardless of the tree's shape, the algorithm consistently achieves O(n) time complexity. For space complexity, it is determined by the depth of the recursion stack, which is directly tied to the tree's height. In the worst case of a completely unbalanced tree, this height is O(n). In contrast, for a balanced binary tree, the height is approximately log n, leading to a space complexity of O log n. Additionally, the single global variable used, self.max_length, only requires O(1) space, making it an efficient component of the solution. The space complexity also involves the local variables used within the DFS function. These include variables like node, parent_val, and length, which are allocated for each call and occupy constant space, O(1). Since these variables are ephemeral and only exist within the scope of a single function call, they do not significantly impact the overall space requirements. Combining this with the recursive call stack, the total space complexity depends on the tree's height. For a skewed tree, where the recursion depth equals the number of nodes, the space complexity is O(n). For a balanced tree, where the height is proportional to log n, the space complexity is O log n. This balance between recursion depth and efficient use of local variables ensures that the algorithm remains space efficient even for larger trees. To further understand the efficiency of this solution, we can compare it to a naive or brute force approach. A less optimized method might involve traversing the tree multiple times to calculate consecutive sequences for each path, resulting in a time complexity of O(n²) in the worst case. In contrast, the DFS solution avoids such redundancy by dynamically calculating sequences during a single traversal, achieving O(n) time complexity. Additionally, the DFS approach uses the call stack efficiently, minimizing the need for extra data structures that could increase space usage. By relying on recursion and a global variable, it achieves a space complexity of O(h), where h is the tree's height. These optimizations make the DFS approach both time and space efficient compared to alternative methods. Finally, let's solidify the time and space complexities with a mathematical proof. For time complexity, let T(n) represent the time required to process a tree with n nodes. For each node, constant work is performed, and the two subtrees are processed recursively. This can be expressed as T(n) equals T, left subtree, plus T, right subtree, plus O(1). Since every node is visited exactly once, the total work is proportional to the number of nodes, leading to T(n) equals O(n). For space complexity, the recursion depth is equal to the height of the tree. In a balanced tree, this height is log n, resulting in O log n space complexity. In a skewed tree, the height is n, leading to O(n) space complexity. These calculations confirm the algorithm's efficiency in both time and space. When tackling problems like finding the longest consecutive sequence in a binary tree, there are several common mistakes to watch out for. First, failing to track state correctly during a depth-first search can lead to solutions that miss critical conditions, such as maintaining a valid consecutive sequence or ensuring nodes are processed properly. Additionally, always account for edge cases like an empty tree, a single-node tree, or trees that are heavily skewed to one side. These scenarios can easily cause runtime errors if overlooked. Another frequent pitfall is confusing traversal orders. Pre-order, in-order, and post-order serve different purposes. For example, if the problem requires processing parent nodes before their children, using post-order traversal would produce incorrect results. Recursion depth is another concern. Large trees can trigger stack overflow errors if the recursion is not optimized. Finally, time complexity is a crucial factor. Brute force solutions might work on small inputs, but they often fail on larger ones. Always aim for an efficient approach that scales well with input size. In interviews, tree problems often test your ability to recognize patterns and think recursively. Many problems can be broken into smaller subproblems using strategies like divide and conquer or aggregating results from subtrees. It's important to identify these patterns early on. Input constraints, such as the maximum depth of the tree or the range of node values, are often left ambiguous intentionally. Interviewers may expect you to ask clarifying questions to ensure your solution handles edge cases correctly. While it's fine to start with a brute force solution to demonstrate your understanding, you should always propose optimizations, such as pruning unnecessary branches or using memoization, to highlight advanced problem-solving skills. And remember, clear communication is just as important as the solution itself. Explain your choice of traversal method and how you account for tricky cases, as this shows both clarity and depth in your thought process. Many related problems can help reinforce the concepts needed for solving binary tree challenges. For example, problems like binary tree maximum path sum or diameter of binary tree share overlapping techniques, such as recursive aggregation of results. Similarly, the longest consecutive sequence problem on arrays and path sum 3 also provide valuable practice with state tracking in different contexts. When it comes to approaches, using depth-first search with state tracking is often a structured way to solve these problems. By maintaining state during recursion, you can handle a variety of conditions effectively, though this approach may require extra memory and careful implementation to avoid bugs. Alternatively, iterative DFS or BFS can help avoid issues like excessive recursion depth and are sometimes easier to debug, but they come with trade-offs, such as requiring explicit stack or queue management, which can make the code more verbose. Dynamic programming on trees is another powerful technique to consider. By storing intermediate results during recursion, you can optimize problems that involve repeated calculations, like finding the longest path or maximum sum. However, implementing dynamic programming on trees can be more complex and challenging to debug, especially for those new to the concept. Another important distinction is between top-down and bottom-up traversals. Top-down approaches are useful for propagating state, such as a running path sum, from the root to the leaves. In contrast, bottom-up traversals are ideal for problems that aggregate results from child nodes to their parent, like calculating the maximum path or determining subtree properties. Choosing the right traversal strategy can make a significant difference in both the correctness and efficiency of your solution. Great job! In this session, we tackled the problem of finding the longest consecutive sequence in a binary tree. We reviewed key strategies, analyzed complexities, and learned some valuable takeaways for similar problems. Thanks for tuning in, and see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!